All right, for today's lesson, we are going to look at graphing proportional relationships and specifically looking at unit rates and using unit rates to graph. So first scenario is that coffee costs $18 for 3 pounds. So $18 for 3 pounds. And I'm going to look at my graph. I'm going to highlight my y-axis. So the vertical axis, as a reminder, is our y, okay? And our x-axis, our horizontal axis, is the x. And I'm going to label these, okay? So maybe, let's see, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We need to go up to 18. So maybe I'm going to have this, each of these represent every other is 3. So this is 3, 6, 9, 12, 15, 18, 21. And then for the x's, I'm going to have them each represent 1, but I'm just going to label every other. 2, 4, 6, 8, 10, 12, 14. Okay. Sorry, that was off the graph or off the video there. So we've got it labeled, and then we're looking at this comparison. We've got $18 for 3 pounds, okay? And as a reminder, it's our ratio of our y, that vertical, over x, the horizontal, okay? So question A says, where can you see the cost per pound of coffee in the graph? So the word per means 1. So we want to know per 1 pound, that is our x value of coffee in the graph. So the cost, what is the cost per 1 pound? So I'm going to graph this information first. We know it costs $18 for 3. So our x value is 3, so I'm going to go to 3, and our y value is 18. So that's going to be up here. And I'm going to draw a line connecting from 0, 0 to 18 over 3. Okay. And you might notice it kind of intersects at a couple other clear points. So what is the cost per 1 pound? If I look, my 1 pound would be right here. And what is that cost? It is $6 per 1 pound. And if we think about that, that is our constant of proportionality, 6 over 1, plus 18 over 3 simplifies to 6 over 1. So the cost per 1 pound is our unit rate, which we can find on the graph there. At this store, for part B, the price for a pound of coffee is the same no matter how many pounds you buy. Let X be the number of pounds of coffee and Y be the total cost of X pounds. Draw a graph of the relationship between the number of pounds of coffee and the total cost. That's what we already did here, okay? So all of this labeled here is we're showing that ratio. It's the same each time. 6 over 1 simplifies to 6. 12 over 2 simplifies to 6. 18 over 3 simplifies to 6, and it would if we continued to this line on further. And then part C, what does the ordered pair 0, 0? So this ordered pair right here, 0, 0, what does that represent? Remember that this first 0 is our X value, which is representing pounds, and the second 0 is our Y value, which is representing the price, the cost. So what that means is 0 pounds of coffee costs $0, which makes sense. They better not be charging you anything for nothing, right? All right. Next scenario is using the graphs to write the unit rate. So we're writing the unit rate given these graphs. as a coordinate 1, r, because the unit rate means for these x values here, for this one we have time in minutes, time in minutes, time in hours, that x coordinate is 1. So we want to know for each of these wherever 1 is, okay? So in this first one, 1 is right here. So we are looking at what would be the x or the y value at unit 1. We know it's going to be 1 for x. What is the y value? For here, it looks like it's halfway between, so that might be hard to pick. But if we go across, the halfway mark in between 2 and 4 would be 3. If you're not positive that that's the correct value, you could find a more distinct value, like right here. I see that y is 6 when x is 2. But if I simplified that, I would also get 3 over 1. So an x value of 1, a y value of 3. For part B. Again, we're comparing the x to the y. So y goes here, x goes here. So our x value, we want the unit rate, so we know x is 1. I'm finding where x is 1, which is right here. X is 1, right there. So we're looking at where does that intersect? This one's a little bit hard because it doesn't actually intersect right at 1. It's less than that. I don't want to make a guess. I could, but there's clear points that I could use to get an accurate amount. So if I go to this clear point, the y value is 3, the x value is 4. So 3 over 4. If I simplify that, if I divide that on a calculator, I get the decimal 0.75 over 1. So when our x value is 1, our y value is 0.75, which looks close to that, right? It's just under 1. And then our last one. Again, remembering our y value in the ordered pair comes second. Our x value is first. We want the unit rate, so we want to know what it is when x is 1. I'm looking on my graph. The x value is 1 right here. I'm going to see where that intersects. It looks like it intersects right here. I need to check where that falls here. These are all going up by 1, so it's 1, 2. It intersects at 2. So that is our examples. Now let's look at independent versus dependent. So our independent variable is a variable whose value does not depend on that of another. It comes first, and specifically what is important to note is it represents the x variable. When you're trying to decide if something is independent or dependent, time is always going to be independent. Hours are always hours. Minutes are always minutes. It's not dependent on something. The other variable that we will see is a dependent variable, which depends on another one. So it comes second, and it represents the y variable, right? We have x comma y. And key words or things that often tell you dependent variables is money and totals are often, maybe not always, but usually are dependent because money is dependent on something. I can't just magically have money appear. I have to work or I have to do something else, right? For totals, that's the total amount is dependent on the other part. So pay, spend, dollar, sell, any of these things that you'd see would tell you dependent variables. And if you're thinking about it in a sentence form, the dependent variable depends on the independent variable. So number 3, we're going to apply this. The table in the graph below display the number of times a baby's heart beats in a given number of seconds. What does the point 7.12, 18 represent? As we've already talked about in a table, the left side is x, the right side is y. So my x is time, which would be here, and that would be my first point here. And our y comes second, that's our vertical axis, and is right there. So 7.12 is referring to the x value, which is time in seconds. So it means 7.12 seconds, comma, 18 is the y, which is representing the beats, 18 beats. So in an actual sentence form, it means the baby's heart beats 18 times in 7.12 seconds. And then which are the dependent and independent variables? So as a reminder, independent is our x, it comes first. Dependent is our y, it comes second. So independent, I'm just gonna write I equals time, specifically in seconds. And our dependent is the number of beats. Last question. Create a bird, we're gonna create this chart. A bird is flying at a rate of 15 feet every 2 seconds. The distance is directly proportional to the seconds. Create a table and graph that could be used to represent the bird's speed. So they already filled in seconds and distance for you, but it makes sense. X goes on the left, Y goes on the right, and as we already discussed, time, which seconds would be part of time, should be independent. So our graph, the time in seconds, is our independent variable. So that means our distance, y, is our dependent variable. So our distance in feet. It gave us the first ratio, 15 feet every 2 seconds. So 2 goes with seconds, 15 goes with feet. And then we can come up with a ton of different scenarios here, right? I'm gonna graph this first, 2 and 15. And then maybe I double it. 2 times 2 is 4, 15 times 2 is 30. So another point could be at 4:30. Maybe I do 2 times 3. So 2 times 3 is 6, and I do 15 times 3 is 45. So another one would be at 6:45. And maybe I do the reverse, okay? Maybe I want to find that unit rate, so I'm going to divide 2 by 2 to get 1, and I'm going to divide 15 by 2 to get 7.5. So we can graph that unit rate right there. And as long as I did all these points correctly, they should all connect in a straight line. If they don't connect in a straight line, that means we did something wrong. Okay? And then what are the dependent and independent variables? So as a reminder, our independent is our x, and time is always independent. So time, specifically in seconds, is our independent. And our dependent is the other variable here, which is our distance, specifically in